Okay.
How about now? Okay.
Okay.
All right, good. So hi, everyone.
Yeah, we are happy to have the last talk of the first day by Nima Anari, and will tell us about counting bases of Matroid.
All right. Hi, everyone. So this is based on joint works with Kui Liu, Shayana Viskaran, and Cynthia Vincent. So let me start with the motivating question behind this talk. And the motivating question is the fundamental question in the community of sampling and counting. What is it that makes some distributions easy to sample from, and what is it that makes some of them hard to sample from, right? So let me give you some examples that some of which we are going to go over in this talk. Okay. So a basic example is spanning trees in a graph. So let's say you have a graph and you want to sample a spanning tree from it uniformly at random. So another example is, let's say from the same graph, you want to sample a subset of vertices that form an independent set. They don't have an edge between each other. And another example that's gaining popularity in the machine learning literature is volume-based sampling. So let's say you have a bunch of vectors and you want to sample a subset of them with probability proportional to the volume formed by those vectors. Okay? So out of these three examples, two of them are actually easy to sample from, and one of them is computationally hard. So spanning trees and volume-based sampling are easy examples, and independent sets in general are hard to sample from. Okay? But the question is there like a property that defines a nice large class of distributions that are algorithmically tractable? And this talk is about one of these nice properties. Okay? So I'm going to show you that the first and the third example both fall into a category of distributions that form that satisfy some form of convexity property. And this convexity property is the reason why these are algorithmically tractable. Okay. All right. This convexity property is actually very delicate. So for example, in the third example, if you change the probability of choosing a subset of vectors from being proportional to volume to proportional to volume squared, then, sorry, my video is, okay. All right, I think it should be better now. Okay. So if you change the probability from being proportional to volume to being proportional to volume squared, then still this convexity property is going to hold. But if you change it to some higher power, some high enough power, this convexity property is not going to hold. And in fact, these distributions, as the power gets large enough, become hard to sample from. Okay. So convexity, you probably know it from the continuous. So the convexity property that I'm talking about is different from the continuous notion of convexity, but you've probably heard of wonderful properties of convexity in the continuous world. The idea behind this new property, this new convexity property, is the same. You're gonna get global guarantees for local algorithms. And let me demonstrate what I mean by that. So in optimization, you've probably, continuous convexity is useful to analyze local optimization algorithms, think of like gradient descent. So the type of convexity I'm talking about, which is a discrete notion of convexity, is going to be useful for deriving global guarantees about the analogous discrete algorithms, namely local search. So, in maybe a little bit less well known is in sampling problems. Still, convexity there is going to is useful in the continuous world. You can sample uniformly at random from convex sets by doing things like grid walk or ball walk. The type of convexity I'm going to focus on today is a discrete analog of this, and we're going to use this property to analyze similar random walks, but in the discrete world. Okay. So just to delve into a little bit more depth, you all know that if you have a convex set and you want to optimize the linear objective over it, then as long as you have some very weak access to this convex set, you can do this. One example of an algorithm that does this is gradient descent, but there are many other things. Some celebrated results initially by Dyer, Fries, and Cannon, and building up to a lot of recent developments, show that you can also sample from convex sets uniformly at random, and you can also count, or in the continuous literature, integrate or compute the volume of these convex sets approximately. So all of these three tasks, optimization of a linear objective, sampling from the set, or computing the volume of the set, are doable for convex sets in the continuous domain. You can even generalize these primitives to non-uniform distributions. So you can do sampling from uniform distributions over a convex set, but you can also sample from non-uniform distributions that are proper generalizations of uniform distributions over convex sets. So if you have a distribution in Rn, which is log-concave, then you can also approximately sample from it, or you can do integration, or you can do inference over it. But what I'm talking about today is the discrete analogs of all of these things. Okay? So if you're looking at optimization problems, there is a well-studied class of discrete objects that are somewhat analogous to convex sets. And these are matroids. So don't worry if you don't know what matroids are. I'm going to go over their definition and give you a bunch of nice examples. So in this talk, I'm going to basically show you matroids. What is the proper generalization of matroids? What is the analog of log-concave distributions in the continuous domain, in the discrete domain? And then I'm going to show you that we can do all of these algorithmic primitives that we could do in the continuous setting, also in the discrete setting. So optimization, it was very long known that you can do linear optimization over a matroid using very simple algorithms like greedy or local search. But sampling and counting from matroids was an open question, and most of this talk is about how we perform these algorithmic tasks. Okay. So let me dive in and give you a bunch of examples of matroids. I'm going to define what matroids are after giving you these examples. Okay. So the first example comes from a problem called network reliability. So imagine that you have a graph, and edges of this graph are going to fail independently of each other with some known probabilities. The problem you want to solve is compute the probability that the whole graph remains connected. So this is known as network reliability. So for example, if these two edges fail, the graph remains connected. If these three edges fail, the graph still remains connected. If these three edges fail, however, the graph gets disconnected. Okay. So to answer this question, to compute the probability that the graph remains connected, what we have to do is basically compute some statistics about this collection of safe failure sets. Okay, so if I collect all of the subsets of edges that are safe, I just have to basically count these subsets. Okay, so you just collect all of these subsets and just compute some statistics about them. Okay, so just a side note. Network reliability, the question of approximately computing network reliability was resolved by Guo and Jerome in 2018. There is a dual problem to this, network unreliability, which is the problem of approximating the probability of getting disconnected. So arguably, this is more interesting, but this is tangential to this talk. So there has been a lot of work on this, initially by Karger, and there's been a lot of improvements over this. I think there is actually a recent improvement by Karger as well, which I forgot to mention here. So Carter 20. Okay, so let me dive into the next example. So the next example comes from a mathematical concept called rigidity. So imagine that you have a graph and you've embedded this graph as some sort of a structure in a Euclidean space. So let's say you've made a structure out of sticks that are joined together at their endpoints. So here I'm dealing with 2D structures, but you can do it in any dimension. So sometimes the structure that you make is going to be rigid. Sometimes it's not. For example, this triangle is rigid because if I apply any forces to it, I can't deform it. If I apply forces to this square on the right hand, I can deform it. So again, a question that you can ask is, suppose you've constructed some structure and some of the links or some of the members of this structure are going to fail. Can you compute the probability that that you remain rigid if you assume, let's say, the links are failing independently with known probabilities? Okay. So again, there is a collection of subsets of links that you have to study, right? So here, if this single link fails, you're fine. If these two links fail, you're not fine, and the structure collapses. Okay. So if you collect again all of the safe edge failure sets, that's a collection of sets. What we want to do is compute various statistics of this collection. Okay. So another example comes from matchings in bipartite graphs. So let's say that you have a bipartite graph. I don't know, servers on one side, clients on the other side. And let's say some subset of the clients show up. We want to see if there is a matching from the clients to the servers. And the servers have, let's say, capacity 1. Okay. So again, some subsets are good, some subsets are bad. The subsets that are good, we want to compute statistics of them. So here, these 3 patients are okay. These 3 clients are not okay. Okay. So another example, which comes from coding theory, is reliability of linear codes. So, so probably the most prevalent form of code studied in coding theory are linear codes. So these are, you can think of them as subsets of a vector space over a finite field, like subsets of f2 to the n, that are, sorry, subspaces of f2 to the n, so given by some set of linear equations. So one of the basic questions you can study here is reliability under erasures. So let's say that you encode some message using some vector x that satisfies this system of linear equations, and then some of the bits go missing. So let's say x2 and x4 go missing. So, so can you basically use this system of linear equations to solve for x2 and x4 in terms of the other xi's? So, so this is known to actually be possible if and only if this corresponding columns of the system of linear equations form a linearly independent set of vectors. Okay. So now, if you want to study the reliability of your code, if you assume that each bit is going to be erased with some known probability, and you want to compute the probability that you can recover from these erasures, what you have to do is compute statistics of linearly independent subsets of columns in this matrix. Okay. So this last example of counting linearly independent subsets formed by a bunch of vectors is actually fairly general. All of the examples I've shown you actually embed into this language. So in all of those examples, you can map the elements in your problem. So let's say in network reliability, you can map each edge of the graph to a vector. In rigidity, you can map each link to a vector. So that the collection of these collections of safe failures that we were studying become linearly independent subsets formed by these vectors. Okay. So here I have an example that's going to stick with us throughout the rest of the talk. So it's 6 vectors in 3D space. And what we want to do is compute various statistics of linearly independent sets formed by these vectors, right? So So for example, this subset of size 3 forms a linearly independent set. You can form all subsets of size 3 that form a linearly independent set. You can form all subsets of size 2 that form a linearly independent set, and you want to basically count these things. Okay. So matroids are a little bit more general than this linear independence. They were actually introduced as a generalization of them. So there are matroids in general are a collection of subsets of a ground set 1 through n. So these are, the nomenclature is that you call these subsets independent sets. The name again comes from linear independence. And basically matroids are defined by abstraction of two axioms that linear independence satisfies. So one of them is downward closure. So if you have an independent set I and a smaller subset J contained in I, then if I is independent, J is also going to be independent. And the more important one is this exchange axiom, which says if you have two independent sets I and J, and I is smaller than J, then there is some element of J you can add to I so that you still remain independent. Okay. So if you abstract out these two axioms, you can form many matroids using these two axioms. Actually, the number of matroids on a ground set of size n is doubly exponential in n, much larger than the number of things you can form by linear independence. But again, the question is, can you count or sample from various independent sets from a matroid? Okay. So note that these two axioms by themselves, it's actually very easy to show. They imply that maximal independent sets all have the same size, and these maximal independent sets are called bases. Again, so if you want, you can actually think of just the linear independence matroids for the rest of the talk. So the names are all coming from linear algebra. Okay. So these bases all have the same size, and what we want to do is just count them. If you can do this, you can also count independent sets of any given size k by just trivial reductions. Okay. So to solve all of our reliability problems, we just want to count independent sets of various sizes k, or equivalently just bases of a matroid. And using some celebrated results, we know that to count these things, it's enough to just efficiently produce uniformly random samples, or approximately uniformly random samples from them. So we're just going to show that we can efficiently sample from the uniform distribution over these independent sets. Okay. So the question of sampling from independent sets or counting them was first asked by Mihai and Vazirani in 1989. And since then, there has been a lot of works on this problem. There's been a long sequence of works trying to solve this for various special cases of matroids. So Federa and Mihai solved it for a class of matroids they call balanced, and we're going to see what that definition is later in the talk. But there is a very special property about this solvable class that doesn't include all matroids. So there has also been a lot of work on an even more special case of matroids, namely spanning trees. So spanning trees fall into this special case, but they're a very particularly interesting case of matroids. So here, for a long time, people knew how to sample in polynomial time from spanning trees in a graph, but the focus has been on improving the running time. So over a long sequence of works, the running time for sampling from uniformly random spanning trees from a graph was brought down to almost linear by Schild in 2018. Okay. So there are some related distributions to matroids, namely this volume sampling that I showed you in the beginning. But these are again some special cases which were handled by various types of algorithms, but they don't include all matroids. The results for general matroids were all either exponential time sampling or an exponentially bad quality of approximate counting. So this changed by this changed in the last couple of years. So by finding a new perspective on matroids, we were able to basically get two different results. And I want to focus on this on the second one, but I'll just mention the first one as well. So we now know that there is a deterministic algorithm that can count independent sets of size k in a matroid within a factor of 2 to the O of k. And by some old results, this is almost optimal. But the more exciting thing is that if you allow randomization, you can actually count the number of independent sets within any desired relative error. So there is an FPRAS for counting. So this talk is going to focus on this second result. And the assumption behind both results is fairly weak. You just have to be able to check whether a given set is independent or not. So this is standard in the literature. You assume you have some access to an independence oracle. So for example, in the linear independence matroids, you automatically have this because you can just do Gaussian elimination and check whether a set of vectors is linearly independent or not in polynomial time. Okay. All right. So Mihai and Vazirani, who asked the question of sampling or counting from matroids, also provided a conjectured algorithm for doing this task. So there is this object you can form from a matroid called the basis exchange graph. So you just put all of the bases or all of the independent sets of size k as the nodes of this graph, and then connect two of them if they differ minimally. So for example, these two highlighted things differ in just two vectors, right? So this vector and this vector are different in these sets, so I connect them. Okay. So Mihai and Vazirani basically conjectured that doing a random walk on this graph rapidly mixes, and then basically you can use a simple random walk on this graph to sample one of the vertices uniformly at random. Okay. So there is a strong analogy between this basis exchange graph and similar results in the continuous settings. So if you want to do optimization over a convex set, you can use many different algorithms. One of them is, let's say, gradient descent. So you start from some point and you do basically local changes in the direction that improves the objective the most. So if you start, if your problem is on a convex set, the end result is going to be the global optimum, right? So you arrive at the global optimal at the end. So the same thing happens if you do these, if you basically replace the neighborhood structure by this basis exchange graph in matroids. So if you want to optimize a linear objective over a matroid, what you can do is you can start from some base or some basis or some independent set of size k, and then just do swaps of one element at a time. So maybe you start from here, you go here, and then you go here, and then you end up here, right? So so doing these swaps of one element at a time is just moving on this basis exchange graph. And matroids are actually known to have basically no local optima. Any local optimum that you arrive at is going to be the global optimum of the linear objective. In fact, you can take that to be the definition of matroids. Matroids are exactly the structures where local search with any linear objective finds always the global optimum. this is a very strong analogy to the convex set setting, right? So an equivalent way of saying this, that local search always finds the global optimum of a linear objective, is to say that another basically cryptomorphic definition of matroids holds. So I gave you one definition of matroids. This is another definition that comes in handy in many other settings. Basically, the alternative definition is that if you form a polytope from the bases of a matroid, where the vertices are just 0, 1 indicators of the bases, then this basis exchange graph is going to be the skeleton of this convex hull. Meaning it's the graph formed by vertices and edges of the convex hull, 0-dimensional and 1-dimensional faces of this convex hull. So a matroid is just any 0, 1 polytope whose edges are super short. They are just, the edges of the polytope are just swaps of one element. Okay. So, okay. So what Mihai and Vazirani conjectured was that this basis exchange graph doesn't have any bottlenecks. So you can at least intuitively believe me that convex sets don't have any bottlenecks. The same result was conjectured by Mihai and Vazirani. Okay, and here is the exact definition of this. So Mihai and Vazirani conjectured that if you split this basis exchange graph into two arbitrary sets, S and S complement, then the number of edges between S and S complement is always going to be at least the minimum of the two sides. Okay? So this is a property that's well known for the hypercube, which happens to be this graph in our example. But Mihai and Vazirani conjectured it to hold for every matrix. And this is something that we proved. This is a corollary of our results. But I want to mention something before moving on, that Mihai and Vazirani actually conjectured this to be true for any 0-1 polytope. So if you form any polytope whose vertices have 0-1 coordinates, and you take the graph formed by 0-dimensional and 1-dimensional faces, they conjectured exactly the same statement to hold. And this more general conjecture is still open. So it has some applications. I can maybe mention them later on Slack, or yeah, if you want to know more about these applications, you can ask me.
And Nima, I'm assuming that it's tight. You cannot get a better bound.
Yeah, I mean this example, the hypercube, is tight. Yeah. So if you divide the hypercube into these two subcubes, the number of edges between them exactly satisfies this. But the result I'm going to show you is actually a little bit stronger. So this is this is actually so we get this by the easy side of Cheeger's inequality. So we show basically a spectral. We show that this graph is a good expander, and then the reverse side of a Cheeger inequality tells you that this also holds. Okay. So this random walk on this basis exchange graph is not always going to converge to the uniform distribution, but because the degrees in this graph are not necessarily all the same. So in general, if you walk on a graph, you're going to converge to a distribution that is proportional to the degrees. In a matroid, it's not necessarily the same that all of these degrees are the same. But all of the degrees are within a polynomial factor of each other. So you can easily fix that to be uniform by doing something like rejection sampling. But nevertheless, what we are going to study is actually a variation of this simple random walk on this basis exchange graph. It's still a random walk on the basis exchange graph, but the transition probabilities are different. So let me tell you what the random walk looks like. So the random walk is between independent sets of size k and independent sets of size k minus 1. Okay? So here I have a picture where I've put all of the independent sets of size k on the top and all of the independent sets of size k minus 1 on the bottom. And I've put an edge whenever there is inclusion. So whenever the bottom set is contained in the top set. So what we are going to study is actually a random walk on this bipartite graph. So what does that mean? So you start from somewhere on the top, some set of size k. You drop one of the elements in this set of size k uniformly at random, right? So that takes you to one of these three sets. And let's say you go to this one. So now you have to go back up. So again, you choose one of the up edges uniformly at random. That takes you to one of these two sets, maybe this one. Okay. So the combination of these two steps is a swap of one element, right? So it's a walk on the it's like taking an edge on the basis exchange graph. But the transition probabilities are not uniform as in the same as was the case for the proposed random walk by Mihai and Vazirai, right? So this random walk actually has a little bit of a nicer structure. In particular, we don't have to do anything to it. The stationary distribution of this random walk is actually going to be uniform. So if you look at the degrees on the top, degrees of vertices on the top, all of the vertices on the top have exactly k outgoing edges. So if you just do this two steps many times, you're going to converge to the uniform distribution on independent sets of size k. Okay. So if you do this, the combination of these two steps for many times, the distribution of where you're located is going to converge to the uniform distribution. So you just have to bound the mixing time. Okay, and the mixing time is how fast you converge to this uniform distribution. So the result that I'm going to highlight today is going to show you that the mixing time is going to be bounded by order of k squared log n. So if you're looking at subsets of size k out of a ground set of n elements, you just have to take these many steps. Okay, and the way we are going to show this is by showing that if you look at the variance of this distribution. So the variance is just, take these numbers to be alpha 1 up to alpha m. Just take the average of alpha I squared minus the expected value of alpha i's squared. So this number we are going to show it's like a measure of distance to uniformity. If all of these numbers are the same, then you're at the uniform distribution already. So this measure of distance we're going to show reduces by a factor of 1 minus 1 over k every time. This is known as showing this multiplicative factor reduction in variance is known as a Poincare inequality.
Nima, just a question from Cliver. How do you choose what element to add in the up phase and the down phase in the random walk? I guess it's
uniformly
the previous slide, yeah.
Yeah, uniformly at random.
Okay.
So in the down step, you just choose uniformly at random, and that the down step is actually very easy to implement because you just have to you have a set of size k, you just choose one of its elements uniformly at random and drop it. The up step is actually a little bit more complicated because you have to try out all elements you can add to this set of size k minus 1. So you just try all of these, check with your independence oracle whether they form an independent set, and out of the elements that do, you choose uniformly at random. Okay. So this reduction in measure of distance gives you this result that you just have to take k squared log n many steps in this random walk. So later, Krayan, Guo, and Musa showed that you can actually show the same thing, but with variance replaced by KL divergence. So KL divergence is also a measure of distance. So the KL divergence between the distribution you have at time t and the uniform distribution. They showed that this measure of distance also exactly shrinks by a factor of 1 minus 1 over k. So I hope to give you an intuition of why this is the same factor for both of these. But the good thing about KL divergence is that the KL divergence of the starting distribution is usually, it's much lower than variance typically, because it's usually logarithmic in this, in the number of independent sets, whereas this one is polynomial in the number of independent sets. So their improved result shows that the mixing time, the number of steps that you have to take, is going to be k log k plus k log log n. So a very mild dependence on n. So later, we managed to actually get rid of this dependence on n. So now we know that you can actually, this random walk mixes in k log k many steps, no matter where you start from. So I won't have time to delve into this result at all. I hope to give you some intuition for these two. But note that k log k is the optimal thing that you can hope for. So in each step of the random walk, you're just replacing one of the uniformly random, one element uniformly at random. So by a coupon collector argument, you need at least k log k element, k log k steps to even to replace all of the vectors in the starting set, right? So unless you are dealing with the very trivial Matroid, this number of steps is also required. So this is tight. Okay. So there is one big caveat with all of these. The big caveat is that I'm only talking about mixing times here and not running times. So in fact, going back to the previous question, to implement each step, you generally need order of n many queries to the independence oracle. And that's mainly coming from the op step, because you have to check for all of the elements you can add to the set of size k minus 1, right? So this is not saying that the running time is going to be k log k, it's just the mixing time, okay? So there are some settings where you can actually improve this, this running time from order of n in each step significantly. So let me give you some of these examples. So let's actually first see what this random walk does on spanning trees, right? So spanning trees was a very well-studied case in the literature. So if you implement naively the same algorithm, here is what it does. You start from a spanning tree in the graph. You choose one of its edges uniformly at random to drop. Now your spanning tree is split into two parts, this part and this part. And now from this cut between the two parts, you choose one of the edges uniformly at random and add it. And you keep repeating this, okay? So the number of steps that you have to take for this to mix is order of v log v. So the number of steps is okay, but unfortunately, each time you have to check order of e many edges to see which one of them are eligible to be added to this from this cut, right? So each iteration takes order of e time. So the overall running time is quadratic in the size of the graph. Okay. So this is much worse than the almost linear time algorithm of Shield. There is actually a very nice trick that you can do to the case of spanning trees. So if instead of deleting first and adding second, you add first and delete second, then here is a random walk that you get. So from all of the edges not in the spanning tree, you choose one of them uniformly at random and add it to your spanning tree. Now you have a spanning tree plus an edge, so it forms a cycle. So here is the cycle. From this cycle, you choose one of the edges uniformly at random and drop it out. Okay. So this is not the random walk I've been describing so far, but it actually is. You just have to change your perspective. So adding and deleting is the same as deleting and adding if you look at the complement of spanning trees, right? So if you look at the gray edges instead of the orange edges, I'm just deleting one of the gray edges uniformly at random and then adding one of them back up, right? And it's a well-known fact that if you look at the complements of bases of a matroid, you still get a matroid. So all of these results do apply, and you get an algorithm that still mixes in time order of E log E. But the good thing with this random walk is that there are some very nice data structures you can use to speed up each step of the algorithm. So there are data structures like link cut trees. There are more Eulerian tour trees and so on that you can use to speed up the running time of each step to just logarithmic in the size of the graph. This is just the amortized time of each step. So this actually does give you a better running time for sampling from spanning trees. You get order of E log squared E. I also just want to mention this in passing that if you don't want to sample from your matroid just one set, but you actually want to produce many sets, then you do get some. Then generically you do get some savings. So if you allow for a pre-processing time, then you can bring the total running time, not mixing time, the total running time to just some polynomial in K and log n. And this has some implications for let's say counting bases of a matroid. Okay. Again, going back to the analogy with continuous sets in the continuous convex sets, the pre-processing step is like the analog of putting a convex set or a log-concave distribution into the so-called isotropic position. So this is a well-known pre-processing step that is still the dominating part of many algorithms for sampling from convex sets. So let me, So the main idea behind this improvement is that as long as you have this pre-processing step, you can narrow your ground set from n elements to just poly k many elements chosen IID from a pre-computed distribution. So instead of each step taking time order of n, it just takes time poly k. Okay. So now I wanna switch a little bit of switch focus a little bit and go into some techniques and proofs, and I want to introduce in particular one of the words in the title of the talk, which is log-concave polynomials. So this discrete distributions, you can generally associate with them a polynomial. So this is the partition function this is known as the partition function in some literatures. So let me introduce this polynomial that I'm talking about. So let's say you have this graph, you're talking about the spanning tree distribution over this graph. What you can do is for each spanning tree, you can form, so let's say I put variables over the edges of the graph, X, Y, Z, W, U, V, W. And for each spanning tree, I just multiply the variables on the edges of the spanning tree and then add these up for all of the spanning trees. Okay. So for example, here is one spanning tree, X, Y, W. I get one monomial. And then I add this up for all spanning trees. The end result is going to be this polynomial. So this polynomial has a lot of nice properties. You can read a lot about the distribution you're dealing with from basically this polynomial. For example, if I want to see what is the probability that this edge X is in a randomly chosen spanning tree, what I can do is I can just compute this logarithmic derivative of my polynomial. So the reason for this is that when you take derivative with respect to X, you drop all of the terms that don't contain X. So the numerator gives you the number of spanning trees containing X. The denominator is going to give you the total number of spanning trees. So this is just the probabilistic term, the marginal of the edge X. Okay. So another way of saying this is that gradient of log G gives you the marginal probabilities of the edges. So you can ask, what about higher derivatives? And higher derivatives also have a meaning. So in particular, the Hessian of log G it's a matrix. It's an m by m matrix, and its entries are going to give you some measure of correlation between various edges. So I've written exactly what the entries of this Hessian are. They are the probability that two edges are jointly in a random spanning tree minus the product of the probabilities. So if these edges were independent, this entry would be 0. It's actually a very well-known property that for spanning trees, all of these entries are going to be negative. So all edges give you a negative value for this quantity. Okay. So in particular, the Hessian of log G, when you compute it for spanning trees, is going to have negative entries. But somewhat less well studied prior to our work was the fact that this Hessian, not only does it have negative entries, but it also has negative eigenvalues. So having negative eigenvalues is the same as saying that this function log G is concave. So that's what I call log concavity of this polynomial. And at least for homogeneous polynomials, you can also visualize this through the graph of the polynomial. So log of G being concave is the same as G having convex contour plots, right? So if you look at the contour plots, so this is like, I don't know, G equals 1, this is G equals 2, these curves. The above side of these curves is going to be always a convex set. That's the same as saying that the polynomial is log concave. Okay? So it turns out that spanning trees have both of these properties because their polynomial has a very nice representation. Their polynomial can be written as a determinant where you associate a positive semi-definite matrix to every edge, and then you multiply each matrix by a symbol assigned to that edge. You add these up, you take the determinant, that's the polynomial for spanning trees. Okay. So whenever you do this with positive semi-definite matrices, the polynomial that you get at the end is going to have both properties. It's going to have negative correlation. Its entries are going to be negative, and it is also going to be log concave. This is a property you can check from determinants. Okay. So this special class of matroids that has been so studied in the literature is the class of matroids that has this property. It has negative correlation. So all prior work on sampling from matroids was basically using this property. Somewhat surprisingly, this property was not very well studied for matroids at all. So just to give you some idea of where log concavity also shows up in other places, these are all very related to each other. So there are actually log concave polynomials that you might have seen in other places. So for example, if in this definition, if you change determinant to volume and you change these positive semi-definite matrices to convex sets, so I'm looking at the volume of the Minkowski sum of a bunch of scaled up convex sets. So that turns out to be a polynomial in these variables, in the scalings. This is a theorem due to, I think, Minkowski, I'm not sure. But the log concavity of it is the same as the Brun-Minkowski inequality, which is so well known and loved in the literature. So Garding showed that that so-called hyperbolic or stable polynomials always have log concavity as well. So these polynomials also have negative correlation, but it turns out that volume doesn't have negative correlation. So volume only has this property, not negative correlation. So there are other polynomials coming from algebraic geometry, which count the number of intersection points of various varieties or generalizations of them called divisors. But I'm not going to go into it. Okay. So as I said, spanning trees have this probabilistically interpretable fact about them, which is that their edges are negatively correlated. If you condition on any edge being inside the spanning tree, the probability of any other edge being inside the spanning tree comes down. So this was actually conjectured to be true for all matroids by Seymour and Welsh many, many years ago. But Seymour and Welsh themselves found a counterexample to this conjecture. So it's not true that all matroids have negative correlation. So we really did have to basically go out of the realm of prior work and switch to this other less studied property, log concavity. So we managed to first show that for every polynomial that you form from independent sets of a matroid, you do get log concavity. And this was the first proof was based on some celebrated results of adequacy to Huhan cats called Matroid Hodge theory. But after a few years, we found some simpler proofs of this fact, and I wanna highlight the basic ideas behind the proof. Okay. So if you are given a polynomial, how do you verify that it is log-concave? So let's say I have this polynomial G given to me. I want to check whether the contour plots are convex or whether the polynomial is log-concave. So first observation is that if you have a log-concave polynomial, if you put in a constant value for any of the variables, it's still going to remain log-concave, right? So that's like intersecting the polynomial with one of these hyperplanes, right? So I put in some particular value for this z-axis variable. The intersections I get are still going to be convex looking, right? If I let this constant go to infinity, I still get convex looking curves, right? So it doesn't matter what constant I plug in, I still get log-concave polynomials. So if you start from a polynomial that has degree 1 in every variable, like is the case for our matroids, if you let this constant go to infinity, in the limit you get the derivative of your polynomial. Basically, all of the terms that don't contain this first variable are going to basically vanish relative to the terms that contain it. So you get that if you have a log-concave polynomial, its derivatives are also going to be log-concave. Okay. So what we showed, and simultaneous to us, basically using similar language, Brandon and Hu showed that the reverse of this is also true. If you start from a polynomial and all of its derivatives are log-concave, then the polynomial itself is going to be log-concave. Okay, so you just have to check that derivatives are log-concave. You end up seeing that the polynomial is log-concave. So this simplifies verification of log-concavity by a lot, because every time you can take a derivative, the degree of your polynomial goes down by 1, right? So you get simpler and simpler polynomials that you have to check, and you can just stop at degree 2. Now, it turns out that for matroids, taking derivatives is actually a very well-known operation in Matroid. It's called the contraction of a matroid by an element. So whenever you take the derivative of the polynomial associated with a matroid, you get the polynomial for another matroid. So this operation of taking derivatives preserves matroidness. So all you have to do at the end is check this statement that the polynomial formed by matroids is log-concave when you're looking at independent sets of size 2, just sets of size 2. Okay. So all you have to do is check this for independent sets of size 2. And it turns out that for independent sets of size 2, you have a lot of nice structure. It's also very easy to check that log-concavity is the same as saying that the Hessian of G has at most one positive eigenvalue, and I want to show you why this statement is true for independent sets of size 2. So I'll show you this for linear matroids, but this holds for all matroids. So if you have a linear matroid, what are the independent sets of size 2 you can form from it, right? So you can basically group the vectors into groups that are parallel to each other. And then an independent set is formed by taking any 2 elements from different groups, right? So here I have 3 groups of parallel vectors, and the independent sets are formed by any edge in this complete multiplied graph, right? So if I take, let's say, this edge, then this means that this vector and this vector form an independent set with each other. So the independent sets of size 2 in any matroid are exactly in correspondence with the complete multiplied graph. And it turns out that Hessian of G, the thing that we have to study, is actually the adjacency matrix of this graph. So it has this structure. So it has a bunch of groups. so within each group, there are no edges, but outside of the groups, there is always an edge, right? And you can actually write this matrix as the all ones matrix minus this matrix of with ones on the blocks of the diagonal. Now this is a rank 1 matrix, and I'm subtracting something PSD from it. So I start from only one positive eigenvalue, and I bring down all of the eigenvalues. So the end result is going to have at most one positive eigenvalue. So that's how you verify log concavity in the case of independent sets of size 2. Okay. So do I have 5 minutes? Or is that pushing it?
Yeah, 3 minutes.
Okay.
We have time. We also need questions also.
Okay, sure. So let me hurry up on this part. So now I want to show you why log concavity, or at least give you some hint of why log concavity implies mixing of the random walk. Now that we know how to verify log concavity. So our random walk was between sets of size k and sets of size k minus 1, but you can also, there is no reason to consider random walks, not consider random walks between sets of size k and smaller sets. So for example, you can do a random walk between sets of size k and sets of size k minus 2. In the extreme case, you can do a random walk between sets of size k and the set of size 0. This one mixes in actually just one step, but it's not efficiently implementable. Because when you go to the set of size 0 to go back up, you have to check all possible combinations of k vectors that you can add. And that's not efficient, right? Now, one less extreme case of that is the random walk between sets of size k and sets of size 1. And this random walk actually is still not efficiently implementable, but it's actually easy. It's much nicer to analyze. So it turns out that if you do a random walk between sets of size k and sets of size 1, you can analyze the mixing time of this random walk by just looking at the steps between sets of size 1. Okay, so if I look at the trace of this random walk on sets of size 1, I get a random walk between just the elements, the n elements of my my matroid, right? So the transition probability for going from one element to another element is actually given by these conditional marginal probabilities. This is the probability of transitioning from I to J. It's just the conditional probability of J given I. And this matrix is actually similar to Hessian of G. So that's why log concavity implies something about this random walk between sets of size k and sets of size 1. Now, I don't have time to go into the details of this. I was hoping I would have more time, but there are phenomenal results coming from the literature on high dimensional expanders that show if you know something about the random walk between sets of size k and sets of size 1, you don't want to just know that it's mixing. You want to know that it's ultra rapidly mixing, meaning that the random walk matrix has a very large spectral gap. Then that implies that the random walk between sets of size k and sets of size k minus order 1 also mixes, but this time only rapidly, not ultra rapidly. So that's an idea coming from the literature on high dimensional expanders. Now the good thing is that these ones are efficiently implementable because in the op step you just have to check a few vectors to add it, right? And for Matroid, it turns out that these random walks between k sets and 1 sets are as ultra rapidly mixing as you can possibly hope for. Again, because of this connection to the Hessian of G. Okay, so let me skip this part. If I have time, I can go back. So let me finish by mentioning some open questions. So one open question is, all of the results I showed you hold for matroids, and in the discrete world, surprisingly, matroids are not the only thing that that are not the only large class of objects that we can optimize over. It turns out that we can also optimize over intersections of matroids. So one very big open question is, can you also sample from intersections of matroids or count the intersections of two matroids? So this is actually equivalent to counting rainbow bases or rainbow independent sets in a single matroid. You can reduce it to this problem generically without loss of generality. You color the vectors in your, let's say, linear independence matroid, and you want to count the number of bases that choose one element from each color. So there are some partial results here, but we're nowhere close to fully resolving this. It turns out that log concavity of the polynomial has actually a nice generalization. So all of the stuff that I told you doesn't hold just for matroids, but it actually goes beyond matroids to other distributions. So instead of requiring the polynomial to be log concave, you want the log of your polynomial when you replace each variable by a fractional power of it to be concave. So this is a soft property. You control it with this parameter alpha. And as long as this parameter alpha remains a constant bounded away from 0, you having this sort of fractional log concavity implies rapid mixing of your of random walks on your distribution. The question is, what are distributions that satisfy this property? Thank you.
Okay. Thank you, Nima. So questions? Okay, so while people are thinking, let me ask a question. So in the random walk, when you have the k sets and the k-1 sets, you said that you drop a random edge and then you may add a random edge and you have to try all possible edges. Why do you, I mean, is it, maybe you only need to do it like choose few at random? Do you really need to check all of them? Or, I mean, is it clear that the edges that you're adding are only a small set, but you need really to check a lot?
So there are graphs where if you choose uniformly at random, then you have to do order of m many tries to be able to add something. For example, if you're let's say your graph is just the union of two spanning trees or a path that is doubled up. Any edge that you drop, you have to add back its basically twin.
Okay.
So simple ideas like that don't work, but of course I can't prove that there is no efficient way of doing this.
And in the process, oh, I see, there is one more question. Can you say more what it means by ultra-rapid mixing time?
Yes.
Yeah.
So ultra-rapid mixing, what I mean by that is this, going back. So there is this matrix coming from the random walk between sets of size 1 to sets of size 1. Ultra-rapid mixing is that without this factor of 1 minus, without this factor of 1 over k, the maximum, so lambda 2 of this matrix is bounded by order of 1. So this means that lambda 2 of the actual probability transition matrix is, so lambda 2 of transition matrix is bounded by order of 1 over k because of the scaling by 1 over k factor. So normally in mixing, you want the lambda 2 of the probability transition matrix to just be slightly away from 1. Here I want it to be bounded by a constant divided by k. And for matroids, the exact constant is exactly 1 over k.
Okay, thank you again. And last question for today: Are there special cases of Matroid intersection that can be captured by your ideas?
So I didn't get a chance to talk about this, but there are some. So as I said, matroid intersection, you can always reduce it to this colored version of basis of a matroid. In some upcoming work with students at Stanford, we've shown that if the number of color classes is constant, and you want to count bases where so you're given some numbers C1 up to CS. You want to choose from each color class Ci many elements. As long as S is bounded by a constant, then then random walks basically mix in that case. But the problem is that even for so there is a very famous special case of Matroid intersection, which is bipartite perfect matchings. This was resolved by Jerome Sinclair and Vicoda. For that case, it's not like a simple random walk like what we've been studying between sets of size k and sets of size k minus 1 that mixes. They have to do a lot of extra clever ideas to get sampling in that case. So we don't even have like a conjectural algorithm here in the general case.
Okay, I would like to thank all the speakers of the day and all the speakers of the session, and we will meet tomorrow. So the invited talks are starting at 12 noon, but there is also contributor talk session that starts at I think 9:45 until 11:30. So please look at the program. These are 3-minute talks, and we will meet tomorrow. Thank you all for attending, and we'll see you tomorrow. Thank you.